So all this talk about similar triangles and similar polygons and similarity, you may wonder, well, man, how can I ever use that? It's kind of interesting because you can do what's called indirect measurement. And it's where you take and you measure the height of something by creating another similar object. So I can tell you this, I can find the height of the ad building by never taking a tape measure to the ad building. Or I can find the height of a tree, or I can find the distance across something. In fact, there's an old, and I don't even know if this is true or not. I've heard this. I would have to verify this story, but there's a story that Napoleon was, out on one of his going to war, taking his army somewhere, and came to a river and couldn't cross it. And they had to build a bridge, but they needed, before they could do anything, they needed to figure out what the distance was across the river. And they couldn't figure out how to do that. And then Private walked up and said, "Hey, Napoleon, I can tell you the distance across the river. I can measure it." And so Napoleon said, "Okay, what do you need?" And the army guy was like, "I don't need anything. All I need is my hat." And he actually measured the distance across the river using his hat, and his hat never left his head. So kind of an interesting story. You can do that too. Maybe you guys will figure it out before class, but ask me during class. And if you ask me during class, I'll explain how that can be done and how you can measure the height of anything. But this is one way. In example number 4, it says a tree outside Ellie's building casts a 125-foot shadow at the same time of day. Ellie casts a 5.5-foot shadow. If Ellie is 4 feet 10 inches tall, how tall is the tree? Okay, so what we have here is we have two triangles. We have this triangle right here. We have this big triangle made with the tree, and the shadow is 125 feet on the ground. And then with Ellie, we have this triangle right here that's smaller. So Ellie makes a 90-degree angle with the ground. The tree makes a 90-degree angle with the ground. And this angle that it is with the sun is same for both of them. So then I have, using the angle-angle similarity postulate, I would have two two similar triangles. So this is the height of the tree, which is x feet. This is the height of the shadow, which is 125 feet. This is the height of Ellie's shadow, which is 5.5 feet. And she is 4 feet 10 inches. Okay, so then here's our first problem here. We just do a proportion, but the first problem is with her height. Her height is in 4 feet 10 inches. So I could say it's 4 and 10 over 12 feet. Okay, because she has 10 inches out of 12 feet. So what decimal is that? So if I say 10 divided by 12, that's going to give me 0.83 repeating. Okay, so what I'm going to do is I need to put everything in feet. So I'm going to change this measurement here to 4.83. And we'll just take it out to the thousandths place. 4.833 feet is Ellie's height. So obviously we have estimated her height. So we'll get really close to the tree's height, but it's going to be an estimate there because I just introduced air into her height because she is 10 feet or 10 inches, and I estimated that to be 0.833 feet instead of 0.833 repeating feet. Anyways, in chemistry, we'll get into that. So I could set this up as saying x over 125 is equal to 4.833 feet as well over 5.5. So then when I multiply here, this is going to be 5 times x, 5.5 times x, which is 5.5x. And that's going to be multiplied, then I multiply 125 times 4.833, and that gives me 604 0.125. Now I just need to divide both sides by 5.5. And when I do that, 604 divided by 5.5 gives me 109.84 feet. So my tree is about 109.84 feet tall.